So this is week 11 of Applied Thermodynamics course. So this week we'll deal with psychrometrics. So why psychrometric study? So to give you a brief idea, the previous week we talked about vapor compression refrigeration system and vapor absorption refrigeration systems and so on for refrigeration and air conditioning applications. We use these cycles. So see, major components we saw that the refrigeration or VCRS cycle consists, and apart from the equipment which is used to build a cycle, namely the compressor and a valve or a capillary tube for expansion, and then you have heat exchanger. So these are the major components you use to build. The other two important interactions which the equipment have is one, which is the refrigerant which is flowing inside this equipment, which is producing this cooling effect. And so that is the refrigerant point of view. The other is the space which you are cooling. So your air conditioners, you are keeping it, you have an evaporator inside that essentially cools the air which is there inside the room. So this air is not just pure air, but it's a mixture. So you have a mixture of nitrogen, oxygen, and so on. These are all dry components, and you also have some amount of moisture present in the air. So even though air, the separate components, nitrogen, everything together, we call it as a dry air. Even though we assume that ideal, but because there's some amount of moisture present, so we need to take care of this to do our calculation and come up with in the design or a rating of any component or the heat exchanger is crucial. So in the evaporator you may have frosting or condensation. So if you see in a refrigerator, in the top portion in the previous single door refrigerator which we used to have, now most of it is a double door, but single door is still available. So we see there in the top compartments where you, the freezer compartment where you keep ice or ice creams and so on, where you need a lower temperature. You see it gets ice formed over it, and we have to manually press a defrost to remove that ice. So this is an again, because the frequent opening and closing of the door, your air is entering there and is getting condensed and frozen on this freezer compartment. So the air is not just air, but you have your dry air and some amount of moisture which is present in the air. So that too need to be studied. So that's why the psychrometric. So there are few terms in psychrometric as wet bulb and your dew point or dry bulb temperature. So dry bulb temperature is your ambient, whatever temperature it's there of the air is, so that's your dry bulb temperature. And if you see wet bulb temperature is if you adiabatically add water and bring it the air to saturation, so that temperature is your wet bulb temperature. So basically how is it measured? So that is the actual thermodynamic definition of wet bulb. It's called a thermodynamic wet bulb temperature, but we cannot so a simpler way of measuring this wet bulb temperature is you have a thermometer, you put a wick or a cotton cloth in the bulb of the thermometer, and this is dipped in the water, and if you rotate it or air flow, and that comes, it will pick up some moisture from it. So there is a mass transfer and the heat transfer, and the temperature will drop, and when it comes to equilibrium, that is called as the wet bulb temperature. So this actual difference between this thermodynamic wet bulb temperature and this wet bulb temperature will be very less. So we generally use this, it's easier to measure also, so we use this wet bulb temperature. and the moisture content in the air is called as humidity, and it's measured in specific humidity. So that is mass of water present per kg of dry air. It's called as specific humidity, and relative humidity is how much mass of water is there compared to when it is in saturation. So that is relative humidity. And dew point temperature is the temperature where you will see the first dew or first drop of condensation of water. So combining this all together, we draw this psychrometric chart. So it's actually an oblique chart where this, you see the saturation line, so there you have a axis called enthalpy axis there, and there's a specific humidity. So this was first drawn by Mollier, so drawing an enthalpy versus specific humidity. So this chart is called as a psychrometric chart. And then you have a dry bulb temperature at as the x-axis or the horizontal axis. So any vertical line, so you have dry bulb temperature will remain same along this vertical line, and you have relative humidity lines which goes along the similar to the saturation lines. There are multiple lines which will be drawn for constant relative humidity, and any horizontal line will specify your moisture content in the air remains same. And the wet bulb line is again shown here. So this there will be multiple wet bulb line, and each of the wet bulb line temperature slope will be constant, and there will be specific volume or volume lines here similarly, and this there will be enthalpy lines which will be running parallel to this wet bulb lines, slightly offset, but it will be running parallel to this wet bulb lines. So this is how a psychrometric chart will look. So, and again this comes for different conditions. So generally what is available is your ambient pressure, and this may not be used for different altitudes and pressure, so you use appropriate charts for or corrections for that. So with this psychrometric chart, let's see what kind of process can happen if we have listed some processes and how that process looks in a psychrometric chart and what happens to that. So sensible heating. So sensible heating is like heating with no phase change. So for say you are having water in a container and you're heating it, you know that water boils at 100 degrees Celsius at atmospheric pressure. So it boils at atmospheric pressure, 100 degrees Celsius atmospheric pressure. So from your room temperature to your atmospheric pressure, your 100 degrees Celsius, what is going through, it's called as a sensible heating. So that process is sensible heating. So there is no phase change, but your water is getting heated, your temperature is rising. So that's a sensible heating process. So how do you denote that in a psychrometric chart? That is given by the OA. So that is your process for sensible heating. So you see here, your the water content in the air remains same because this is horizontal, so specific humidity will remain same. Specific humidity, as I told, is the mass of water divided by your mass of dry air, or mass of water per kg of dry air. This is specific humidity. So your specific humidity will remain same, but your temperature is rising. So this denotes a sensible heating. And similarly, if your temperature is dropping and specific humidity is same, it's called as sensible cooling. So once this hits your dew point this here, that's your dew point temperature. So from there condensation will start happening, then it will follow the saturation line. And third is humidifying. So humidifying is process OC. So in this case what happens, your temperature is same, but the water is getting picked up. So just like for your drying cloths, so and your so water content is picked up in atmosphere, but the atmosphere temperature is same. So kind of your temperature is same, but this water content in the air is varying, so that is humidifying. And similarly dehumidifying is removing water from the air with constant temperature. Then similarly heating and humidifying is denoted by OE. So your heating, so temperature is rising, and then humidifying, so your specific humidity will rise. So connecting this two process is your heating and humidifying. And similarly cooling and dehumidifying, and so on other. So you have to just go along a direction for heating and then humidifying or dehumidifying. So that will give you the process. So these are generally the process which you will encounter. So with that we'll move on to some MCQs. So the first one is the wet bulb temperature at 100% relative humidity is dash dry bulb temperature. A lower than, B higher than, C equal to, D twice. So answer is equal to. So if you have 100% relative humidity, so this is your saturation line, so that also specifies it's saturated. So 100% relative humidity. Relative humidity is mass of water by mass of water at saturation, or specific humidity by specific humidity at saturation. So if you see at that point, your dry bulb temperature also coincides with the wet bulb temperature, so that is equal to. So answer is option C, equal to. So the wet bulb temperature at 100% relative humidity is equal to dry bulb temperature. The next one is the specific humidity decreases during cooling and dehumidification process. So this is true or false question. So it can be either true or false. So question is specific humidity decreases during cooling and dehumidification process. So which is so cooling is a process where your temperature is decreasing, dry bulb temperature is decreasing, or the air temperature itself is decreasing, and dehumidification is you are removing water. So and so you are removing water from the air, so the water content in the air will reduce. And specific humidity is nothing but your mass of water divided per kg of air. So if that is decreasing, that means the dehumidification reduces your specific humidity. So this is true. The next question is dehumidification will take place along with cooling if moist air flows over cooling coil whose mean surface temperature is below the dash of the entering air. So dehumidification will take place along with cooling if moist air flows over cooling coil whose mean surface temperature is below dash of the entering air. A dew point temperature, B dry bulb temperature, C wet bulb temperature, and D atmospheric temperature. So this we have seen. So we need to do a dehumidification. So you see we have discussed about dew point, where the first condensation of the dew drop is happening. So that's where your water is from the air is getting condensed. So water is getting removed from air. So the water as a vapor form in the air as a mixture with air is now condensed. So the net quantity of water in the air will be reducing. So we need a condensation. So for that to happen, your temperature should be at dew point temperature, or else it will not condense. So the answer is A, dew point temperature. So dehumidification will take place along with cooling if moist air flows over cooling coil whose mean surface temperature is below dew point temperature of the entering air. question is, in case of cooling tower, water is cooled by the process of evaporation. First is true, B false. So what happens in a cooling tower is, you have fans which will create flow from bottom to top, and from top you are sending water and sprinkling it, so the water droplets are falling down due to gravity, and then there is air which is flowing in the opposite direction. So what happens is, the water is at higher temperature and you want to cool it. So in the process, the air which is coming in contact with the droplets will pick up some of, because the air is not saturated, it will pick up some water, and it will go away. So what this does is, because the air is not saturated, it needs some water. It can accommodate till it reaches saturation temperature. So the water droplets will take energy from the water droplet itself, so that for it to be converting it to vapor, so the water droplet temperature will go down and some amount of water will convert to vapor and go with air. So you are losing some amount of water in the process, but your temperature of the water falls down and you can go till your wet bulb temperature. So that's the minimum temperature which you can reach for the water. So in this case, your water is getting cooled, and this is happening because of the process of evaporation of water. So answer is option A, true. Next is, evaporative cooling takes place nearly at constant dash. A, dry bulb temperature, B, wet bulb temperature, C, dew point temperature, D, atmospheric temperature. So answer is option B, wet bulb temperature. So this is similar to what I said in the previous case of cooling tower. So this will follow the same wet bulb line. So this evaporative cooling happens. It's a cooling and humidification process. So your water is getting evaporated in the air and it's reaching saturation, and that can go till your water temperature temperature becomes wet bulb temperature. So it follows the wet bulb line temperature line. So your constant in this case is your wet bulb temperature. So answer is option D. The next is, the difference between dry bulb temperature and wet bulb temperature is known as, so your difference, so dry bulb temperature we know what is your air temperature, and wet bulb temperature is your when the wet wick, when it's equilibrium with the air, so that is your wet bulb. So this difference, so wet bulb temperature will always be lower than your dry bulb temperature, so there is a depression. So and there is always a difference between this, and wet bulb temperature is, as I told, is it lower than dry bulb temperature, so it's called as wet bulb depression. So answer is option C, wet bulb depression. So this difference between dry bulb temperature and wet bulb temperature is known as wet bulb depression. The next is a true or false question. In cooling tower, the term approach is the temperature difference between the inlet temperature of water and wet bulb temperature of inlet air. So as I told, the cooling tower, what's happening is you're sprinkling water, and air is flowing from top, and air is flowing from bottom to top, and in the process, because there's a difference in temperature and your saturation, So water is evaporating, some amount of water is getting evaporated and making the air saturated. So this is equivalent to what we saw is the thermodynamic wet bulb definition, having adiabatic saturation process. So similar to that. So and the minimum temperature it can reach is the wet bulb temperature. So this temperature difference is called as the approach. So whatever inlet temperature of water is there, and the minimum it can go is the wet bulb temperature. So that is called as approach, how close it can approach to that. So this difference is called as approach. So answer is A, true. The next question is the minimum temperature to which moist air can be cooled under ideal condition in spray washer is so the minimum temperature to which moist air can be cooled under ideal condition in spray washer. So spray washer is nothing but similar to your cooling tower. So or you can say your air coolers. To say that is similar to your spray washer. You are spraying air, water, and you are flowing air. So the minimum temperature it can cool that air is your wet bulb temperature. So that is the minimum. That's the equilibrium temperature which can be reached between the water and the air. So that temperature is your wet bulb temperature. So even air can only reach your wet bulb temperature. So answer is option C, wet bulb temperature. So the next question is, for a typical sample of ambient air at 35 degrees Celsius and 75% relative humidity and standard atmospheric pressure of 1.013 bar, the saturation pressure of water vapor at 35 degrees Celsius is 0.056 bar. The amount of moisture in kilogram per kg of dry air will be approximately dash. So break it down. What is given is, we have a ambient air. This air is at 35 degrees Celsius and 75% relative humidity. So assuming it's all in atmospheric pressure, so 35 degrees Celsius and 75% relative humidity. Next they are saying that saturation pressure for water vapor corresponding to this temperature is 0.056 bar. So we need to find out the amount of moisture, so in kg per kg of dry air. So we'll see how to solve this. So what is given is dry bulb temperature, which is 35 degrees Celsius, and your phi is 75%. So we know the total pressure, so ambient pressure 1.013 atmosphere or bar, and Psat is at 35 degrees Celsius is 0.056 bar. So your relative humidity is nothing but your vapor pressure divided by saturation pressure. So from this you can find out your vapor pressure of air at 75% relative humidity. So it will come out to be 0.042 bar. So now we know So your phi is your relative humidity. So relative humidity is expressed as vapor pressure of air, so the current air condition divided by the saturated vapor pressure. The saturated vapor pressure is given at 35 degrees Celsius is 0.056 bar. So from this we can find out the vapor pressure will come out to be 0.042 bar. So from using this, the relative humidity is expressed as 0.622 into your vapor pressure divided by your total pressure minus vapor pressure of air. So that is your vapor pressure corresponding to air divided by your pressure corresponding to air. So water vapor pressure divided by your air pressure. So 0.622 in, so into substituting the values, you will get omega as 0.027 kg per kg of dry air. So answer is option B. In this, the next question is the ambient pressure, temperature and relative humidity of air at location are 101 kilopascal, 300 Kelvin and 70% respectively. The saturation pressure of water vapor at 300 Kelvin is 3.6 kilopascal. The specific humidity in gram per kg of dry air of air is dash. So just like the previous case, here it's given in Kelvin temperature. So your temperature and your relative humidity is given just like the previous one. So it's simpler. You have to just follow the previous example and solve it. So answer is 15.9 grams per kg of dry air. So previously we got in kg per kg of dry air. So here we are converting it to grams. So your total pressure is 101 kilopascal, temperature is 300 Kelvin and relative humidity is 70%, and your saturation pressure corresponding to 300 Kelvin is 3.6 kilopascal. So just like the previous case, your relative humidity is vapor pressure divided by the saturated vapor pressure. So substituting the values, we get vapor pressure as 2.52 kilopascal. So omega is 0.622 into vapor pressure divided by your partial pressure of air. So omega, substituting the values, omega comes out to be 0.0159 kg per kg of dry air. So converting it to gram, you will get 15.9 gram per kg of dry air. So with that, move on to the next question. 1 cubic meter of hydrogen at 1 bar and 25 degrees Celsius is mixed with 1 cubic meter of nitrogen at 1 bar and 25 degrees Celsius. For the mixture at the same condition, find mole fraction of components, partial pressure of components, C mass fraction of components, D molecular weight of the mixture, E gas constant of the mixture, F volume of the mixture. So you have 1 cubic meter of hydrogen at 1 bar and 25 degrees Celsius. It is just getting mixed with 1 cubic meter of nitrogen at 1 bar and 25 degrees Celsius. So we need to find out what is the properties in this mixture. So we have to find out mole fraction, partial pressure, mass fraction, molecular weight, gas constant and volume of the mixture. So we'll start with first we'll write the molecular weights for the molar mass. So it's basically molar mass, we call it weights. So molar mass of hydrogen is 4.003 and molar mass of nitrogen is 28.02. So the individual gas constant for this components for hydrogen, so we are denoting hydrogen by 1 and nitrogen by 2. So the hydrogen gas constant is your universal gas constant divided by the molar mass, so 8.3143 divided by 4.003, this gives you 2.077 kilojoule per kg Kelvin. And similarly for nitrogen, it's universal gas constant by molecular weight of nitrogen, which gives you 0.2967 kilojoule per kg Kelvin. So this is the individual gas constant for the hydrogen and nitrogen. Now we need to find out the mass, individual masses in which they are getting mixed. So assuming these two gases are ideal, so we can write ideal gas equation PV equals to mRT. So from that we can find out the mass for individual gases. So mass of hydrogen is P1V1 by R1T1. So here R is your gas constant, which we have already found out. So substituting the other conditions are given. The initial pressure, volume and temperature is given. So volume is 1 meter cube, pressure is 1 bar, and temperature is 298 Kelvin. So substituting, you will get mass as 0.1616 kg. And similarly for nitrogen, we are using the same expression. So P2V2 by R2T2. Substituting the values here will give us mass of nitrogen is 1.13 kg, 131 kg. So the total mass of the mixture when we are mixing this hydrogen nitrogen is 1.2926 kg. So this is in mass basis. So now we will convert this into moles. So moles is nothing but mass divided by your molar mass. So the number of moles of hydrogen is your mass of hydrogen divided by the molar mass. So it gives us equals 0.0404 moles of hydrogen is getting mixed with nitrogen. Similarly, M2 by M mass of nitrogen divided by molar mass of nitrogen comes out to be 0.0403. So we see, even though there is a much difference in mass, the moles are equal. So if you see, it's equal to PV equals to nRT. So your pressure is same, volume is same, and your temperature is same. So for a given fixed volume at pressure and temperature, the number of moles in the occupied in the volume is same, is given by Avogadro's. So if you see this, we have seen that your moles are also same. Substituting, you will get N is 0.0807. The small difference is because of the round off which we have been using. So because of there is a small difference. So with this we can find out the mole fraction and mass fraction. So mole fraction is nothing but the individual mole of the component divided by the total moles of the mixture. So the mole fraction of hydrogen is N1 by N. So because both are having equal moles mixed together, so your mole fractions will also be half. So 0.5 and 5. So that says that equal proportion of gas is being mixed. Next is partial pressure. So partial pressure is nothing but your mole fraction into your mixture total pressure will give you the partial pressure of that component. So since here the mole fractions are same, so the partial pressure exerted will also be same for each of the components. So hydrogen is 0.5 bar. So since the total pressure is 1 bar, so the individual partial pressures will be 0.5 bar and 0.5 bar. So the mass fraction is again similarly the mass of the component divided by the total mass. So here comes out to be 0.125 for hydrogen, and the mass of nitrogen divided by total mass is 0.875 for nitrogen. Next is we need to find out the molecular weight of the mixture. So molecular weight is nothing but since so that's mole fraction into molecular weight plus the summation of mole fraction into molecular weight. So that will give you the molar mass of the mixture. So the summation of individual mole fraction into molar mass of that component. So substituting the values, so 0.5 into 4.003 plus 0.5 into 28.02 for nitrogen gives you 16.01. So this is the molar mass of the mixture. So with this mixture, now we can estimate the gas constant R. So R is universal gas constant divided by molecular weight. It comes out to be 0.5193 kilojoule per kg Kelvin. Next is we need to find out the volume of the mixture. So again, same with PV equals MRT, your temperature and pressure being same, and mass is now the total mass into your molar mass. Substituting that, we will find out it's 2 meter cube. So other way of understanding this 2 meter cube is we are assuming these two gases are ideal, so they don't have any interaction between the two. So for the partial pressure being 0.5 bar, so for that to happen, your volume has to be doubled for the given temperature, and for your pressure to be half, the volume has to be doubled. So that is happening because we are adding 1 meter cube and 1 meter cube. So total volume is becoming 2 meter cube, and in that process your volume is expanding and your pressure is dropping to 0.5. Question is, in a dew point apparatus, a metal beaker is cooled by gradually adding ice water in a dew point apparatus, a metal beaker is cooled by gradually adding ice water to the water initially at room temperature. So the moisture from the room air begins to condense on the beaker and its temperature is 12.8 degrees Celsius. If the room temperature is 21 degrees Celsius and the barometric pressure is 1.01325 bar, find the partial pressure of water vapor in the room air and parts by mass of water vapor in the room air. So we need to find out partial vapor pressure and specific humidity. So what basically is happening, you have metal beaker which is cooled by gradually adding ice water to the water initially at room temperature. So when this so this is similar to example when you are keeping a glass containing ice water, you see that outside there is a water getting condensed which is forming. So that is what is being done here. So this here you are gradually cooling the water, so your temperature of the beaker is also changing in the process, and you are estimating at what temperature the water is getting condensed to estimate the dew point. So that is the idea, to find out the dew point. So you have initially water which is at 21 degrees Celsius, so you are pouring ice water now, and this mixture's water temperature will vary with the proportion of ice water being added. So from 21 it will gradually drop, and once it reaches 12.8, you see that moisture is forming on the outside of the container. So that is the idea. So with this we need to find out the partial pressure of water and the specific humidity. So we'll see how to solve this. So partial pressure of water vapor at dew point temperature of 12.8 degrees Celsius is 1.479 kilonewton per meter square. So that is the partial pressure of water vapor. So that is the vapor pressure of water. So the partial pressure of dry air for corresponding to this condition is your total pressure minus your partial pressure of water vapor. So give you 99846 Newton per meter square. So the specific humidity omega is mass of water vapor divided by mass of air, which can be expressed as 0.622 into the partial pressure of water vapor divided by partial pressure of dry air. Substituting this pressure values, we will get the specific humidity as 0.009214 kg per kg of dry air. So we need parts by mass of water vapor or the total mixture. So in this case, so a mass of vapor divided by mass of the mixture. So mass of mixture is mass of vapor plus mass of air. So that will come out to be omega by 1 plus omega. So this equals 0.00913 kg of water vapor per kg of mixture. So next is a question: a mixture of dry air and water vapor is a temperature of 21 degrees Celsius under a total pressure of 736 mm of Hg. The dew point temperature is 15 degrees Celsius. First, find partial pressure of water vapor. 2. Relative humidity. 3. Specific humidity. 4. Specific enthalpy of water vapor by the three methods of figure. 5. Enthalpy of air per kg of dry air. 6. Specific volume of air per kg of dry air. We'll see how to solve this. So we have a mixture of dry air and water vapor at temperature 21 degrees Celsius, and they are saying dew point temperature is 15 degrees Celsius. So we'll see how to solve this. So essentially what we are, our condition is, we are at point A. So this is our actual temperature, this is 21 degrees Celsius, and since this is dew point temperature, so that is the point where the first water vapor condenses, so, or the saturation. So you go along this line at constant pressure of water vapor. So G, so that is the pressure where your water will start condensing. So that is your dew point temperature. Corresponding temperature is your dew point temperature. So with this, what is known, we will find out the rest of it. So first is, you need to find out the partial pressure of water vapor. So corresponding to this dew point temperature, the pressure corresponding to that will be your partial pressure of water vapor. So it is 12.79 mm of Hg, or 1707.5 Newton per meter square, or 1.7 kilonewton per meter square, or kilopascal. So then second is, you need to find out the saturation pressure of water vapor at 21 degrees Celsius. So the saturation pressure is nothing but the same point C here, denoted here. So that is your saturation pressure corresponding to this temperature. So that is 2489.8 Newton per meter square. So relative humidity is 5 by PV by PS. So that gives you your vapor pressure now is 12.79 divided by 18.65. So this comes out to be relative humidity as 68.58%. So now the specific humidity is again omega is 0.622 into vapor pressure divided by the partial pressure of dry air. So substituting that, so your partial pressure of dry air can be expressed as total pressure minus your vapor pressure of air. So substituting the values, you will get 0.011 kg of water vapor per kg of dry air. So that is your specific humidity. Next is you need to find out latent heat of vaporization of water at dry bulb and dew point temperature. To find out the enthalpy at 41 at point A. So what we are doing is, first we need to find out the latent heat corresponding to 15 degrees Celsius and 21 degrees Celsius. So those values are 2452 kg per kilojoule per kg for 21 degrees Celsius and 2466.2 kilojoule per kg from 15 degrees Celsius. This you will get from a stream table. Then the HC value is so if we go along this first process HC, so from HC to HA, so you have at 21 degrees Celsius, so latent heat added plus, or you can straight away find out the enthalpy at state C, plus you can do the sensible heating to process C to A, so that is Cp into delta T. Or in this case what is done is, we are taking 0 as the reference temperature, so we are sensibly heating from 0 degrees Celsius to 21, and so what is that temperature difference? So Cp into delta T plus your latent heat at C, so that will give you 2540. Similarly, if you follow the process A line, so 0 to F and F to G and A, so in this case we have there is sensible heating of water, and then phase change, and then sensible heating of water vapor. So we have to do that. So if you we do that, Cp of water into the delta T, so 0 to 15 plus phase change plus 1.88 is the Cp of water vapor into the delta T there. So that will give you 2540.3 kilojoule per kg. And similarly, the other way is 0 degrees Celsius, phase change is 2501 plus the Cp of air into the Cp of water vapor into the temperature difference. So that will also give you 2540.5 kilojoule per kg of water vapor. So next is enthalpy of air using the value of specific enthalpy of water vapor from the empirical relation. So enthalpy of the mixture is enthalpy of dry air plus your specific humidity of air into enthalpy of water vapor. So what we have found out is 2540.5 into specific humidity plus enthalpy of air is Cp into the temperature delta T. So Cp of air is 1.005 and the temperature difference, reference temperature being 0, so temperature difference is 21. So substituting, we will get the enthalpy of air as 49 kilojoule per kg of dry air. So next is the specific volume of air is equal to the volume of 1 kg of dry air or 0.01 kg of water vapor. So based on the dry air part, so specific volume is RA into T by PA. So RA is 287.3 for air into your temperature 273 plus 21 divided by your pressure, the partial pressure of air, which is 723.21 into conversion, so rho GH, so it will come out to be 0.875 meter cube per kg of dry air. next question. You need to calculate humidity ratio, dew point temperature, density, and enthalpy of atmospheric air if the dry bulb temperature is 35 degrees Celsius and wet bulb temperature is 23 degrees Celsius. And the parameter reads 750 mm of Hg with relative humidity of 36%. So this again similar problem. So relative humidity is expressed as the water vapor pressure divided by saturated pressure into 100. So substituting that, we know relative humidity is 36%. So from there we can find out your vapor pressure. So humidity ratio is vapor pressure divided by partial pressure of air into 0.622. So substituting here, you get humidity ratio as 0.01285 kg of water vapor per kg of dry air. So your dew point temperature is so corresponding to this saturation pressure. So water vapor pressure, what is the temperature? So that will give you the dew point temperature. So that is 17.7 degrees Celsius. So the partial densities of the mixture is rho A is PA by rho A RAT and rho B by is PV by R rho BT. So the corresponding densities will get 1.1086 kg per meter cube and 0.014 kg per meter cube. So the enthalpy is given as CP plus omega, Cp of air into T plus omega into your enthalpy of water. So 2500, so that is a phase change, a latent heat at 0 degrees Celsius plus Cp of water vapor into temperature. So that will give you the enthalpy. Substituting, we give enthalpy, total enthalpy of air is 68.15 kilojoule per kg of dry air. So next we will go into process. So it's a cooling and dehumidification of moist air. So moist air at standard atmospheric pressure is passed over a cooling coil. Show the process on a psychrometric chart. Determine the amount of heat and moisture removed per kg of dry air. The inlet and exit states are as follows. So number, state, dry bulb temperature and relative humidity is given for the both starting and end process. So inlet is at 30 degree dry bulb temperature and relative humidity of 50, and exit is at 50 and 80 degrees 80% relative humidity. So we will see how to represent this process in a psychrometric chart. So this is what is happening here. So you have a cooling coil, so where your refrigerant is flowing, and over this you have fins and your air is flowing over this. So and because this temperature is lower than your dew point temperature, some of the water vapor will condense and it's collected below. So this is similar to what's happening in the evaporator or in the split air conditioner inside. So if you see, there is always a water dripping outside. So this the process is similar. So there is moist air which is coming in at 25 degrees Celsius and 50% relative humidity, and some amount of water is getting condensed, and in the process also gets cooled, and it comes out at 15 degrees Celsius and 90% relative humidity. So if you see, this is a psychrometric chart given. So the first state point is given as 30 and 50%. So we go along the dry bulb temperature of 30 degrees Celsius. So we go vertically, the straight line from 30 degrees Celsius, and the point where it crosses the 50% relative humidity line, so that's our state 1. So that is my inlet condition. And similarly, exit is dry bulb temperature of 15 degrees Celsius and 90% relative humidity. So using similarly, we can find out state 2. So if the straight line from 1 to 2 is my process, and if we extend it, we can find out the dew point temperature. So adiabatic dew point temperature is represented by S. So where this line crosses, so that is my dew point temperature. and if you see that dew point temperature is 10 degrees Celsius. So where the saturation curve and this line crosses, that is 10 degrees Celsius. So now consider air around the cooling coil as forming the control volume in which moist air enters at 1 and leaves at 2. So the condensed moisture leaves at 3. So applying continuity equation, we have moist air coming in, and then air which is going out, and then some water is coming out. So there is this three process which is happening. So we can do individual mass balance for dry air and the water. So the dry air in the process it remains same. So what is coming in is going out, but water, there is some amount of water which is getting condensed. So that is given by the difference in specific humidity into mass of air. So that is the amount of water which is going out as 3. So if we write a steady flow energy equation, so Q dot E plus M dot E H1 is what is heat which is coming in input, equals M dot A H2 plus M dot W3 H W3. So if you write it in terms of per kg of dry air, so Q plus H1 equals H2 plus omega 1 minus omega 2 into HW3. So H1 we can write it as HA1, which is dry air, plus omega 1 HV1 equals again H2 as HA2 plus omega 2 HV2 plus omega 1 minus omega 2 into HW3. So the W3 is saturated liquid. So the saturation pressure of water at 25 degrees Celsius and 15 degrees Celsius from steam table are. So saturation pressure at 30 degrees Celsius is 4.246 kilopascal, and at 15 degrees Celsius is 1.7051 kilopascal. So from there you can find out vapor pressure is 2.123 kilopascal at start, and at the end of the process is 1.3641 kilopascal. So with this we can find out the specific humidities. So substituting there we can find out the specific humidities. So at inlet is 0.01331 kg of water vapor per kg of dry air, and at the exit is 0.00849 kg of water vapor per kg of dry air. So the specific enthalpies of water vapor and condensed moisture are, so HV1 is your saturated vapor at 30 degrees Celsius, which is 2556.3 kilojoule per kg, and similarly HV2 is the saturated vapor at 15 degrees Celsius, which is 2528.9 kilojoule per kg, and your water is at saturated liquid temperature or at 15 degrees Celsius, which is 63 kilojoule per kg. So now substituting these all values in the steady flow energy equation, we can find out the cooling capacity or cooling provided by the cooling coil, which comes out to be minus 27.3 kilojoule per kg of dry air. So this is negative because it's not heat added but heat removed. Moving on, next question is a 5 meter by 5 meter by 3 meter room contains air at 25 degrees Celsius and 100 kilopascal at a relative humidity of 75%. So determine A, the partial pressure of dry air, B, the specific humidity, C, the enthalpy per unit mass of the dry air, and D, the masses of the dry air and water vapor in the room. So we need to assume constant pressure specific heat for air is given, and for water 25 degrees Celsius. We have saturation pressure as 3.1698 kilopascal, and your corresponding saturated vapor enthalpy as 2546.5 kilojoule per kg. So this is similar to what we did till now. So you can find out partial pressure of dry air from the relative humidity. So we need to find out the saturation pressure corresponding 25 degrees Celsius, which is given 3.1698. So from that we can find out the partial pressure of dry air, and from there we can find out, we know the total pressure, so we can find out specific humidity omega 0.622 PV by P minus PV, and we can also find out enthalpy per unit mass of dry air. So enthalpy is again Cp into T, 1.005 into 25 plus your omega into 2500 plus 1.88 into temperature 25. So that will give you the enthalpy, and we need to find the mass of dry air and water vapor in the room. So that also, so this is what, as I told, we have finding out the vapor pressure or partial pressure of water in air, which is 5 into saturated pressure, so that gives you 2.38 kilopascal. So your partial pressure of dry air is 97.62 kilopascal. Using this we can find out specific humidity 0.62 PV by P minus PV. It will give you 0.0152 kg of water vapor per kg of dry air, and then enthalpy is enthalpy of air plus omega in specific humidity into enthalpy of water vapor. So enthalpy of air is Cpt, and omega into enthalpy of water vapor is given here, so you can straight away use that 2546.5, and then substituting it here gives you 63.8 kilojoule per kg of dry air. So next is both the dry air and the water vapor fills the entire room completely. Therefore, the volume of each gas is equal to the volume of the room, which is 75 meter cube. So the mass of the dry air and the water vapor are determined from the ideal gas relation applied to each gas separately. So mass of air is PV by RT for air, so PAVA by RET. Substituting that, we will get mass of air is 85.61 kg, and mass of water vapor is partial pressure of water vapor into the volume divided by gas constant for water vapor into T. So substituting that here, we will get 1.30 kg. So the mass of water vapor is omega times of mass of air. We can find it the other way around here also, so it will give you the same value of 1.30 kg. So next is a stream of moist air at 2 degrees Celsius dry bulb and 80% relative humidity mixes with another stream of moist air at 30 degrees Celsius dry bulb and 10 degrees Celsius dew point in the ratio by mass of one part of the first to the two parts of the second. So we need to calculate the temperature specific humidity of the air after mixing. So we have two streams of air which is getting mixed at different temperature. So we need to find out the final temperature. So we will find out the individual properties first for each of the streams. So for the first stream, for the given condition of 2 degrees Celsius and 80% relative humidity, your specific humidity is 0.035 kg of water vapor per kg of dry air, and enthalpy is 10.78 kilojoule per kg of dry air, which So this can straight away get it from the psychrometric chart. Next is the mass of dry air per unit mass of moist air. Yes. So mass of dry air is 1 plus omega 1 . So that is mass of air by mass of dry air by mass of mixture. So that will give you 0.9955 kg. So that is the mass of dry air which is present. So for the second stream, similarly for this given conditions of 30 degree Celsius dry bulb and 10 degree Celsius dew point. So here also we can, if you want, we can find the process, but easier is to find it from the psychrometric chart. So that will straight away give you omega is 0.00765 kg of water vapor per kg of dry air, and H2 is 49.67 kilojoule per kg of dry air. So mass of dry air per 2 units mass of moist air is 1.9848 kg. So we are assuming it first is 1 kg and second is 2 kg. So out of which 0.955 kg of air is dry air, and in second case it's 1.9848 kg of dry air. So if we are assuming the mixture enthalpy is mass of the first into enthalpy of the first plus mass of the second into enthalpy of second divided by the total mass, will give you the enthalpy of the mixed stream is 36.68 kilojoule per kg of dry air. Similarly, specific humidity is mass of water plus mass of water of the second divided by the total mass. So that's what is happening here. So that comes out to be 0.00627 kg of water vapor per kg of dry air. So that is omega. So with these two property in prime psychrometric chart, we can estimate any other property which is required. So here we are need to find out the temperature and specific humidity. So with this corresponding to enthalpy and specific humidity, we can find out the temperature. So with this, the next question is moist air enters a chamber at 5 degrees Celsius dry bulb temperature and 2.5 degrees Celsius thermodynamic wet bulb temperature at a rate of 90 cm or cubic meter millimeter cube. The barometric pressure is 1.01325 bar while passing through the chamber. The air absorbs sensible heat at the rate of 40.7 kilowatt and picks up 40 kg per hour of saturated steam at 110 degrees Celsius. So determine the dry and wet bulb temperature of the leaving air. So what is happening is the heating and humidification process. So we'll see how to solve this. So your wet bulb temperature is given is 2.5 and dry bulb temperature is given, and the flow rate is given air, and the barometric pressure is given, and we are given the heat load which is applied, and then also the amount of water is getting added into the stream. So we need to find out the final dry and wet bulb temperature of the leaving air. So this is how the process looks in a psychrometric chart. So your dry bulb temperature is 5 and your wet bulb temperature is 2.5. So you are going along the wet bulb line, constant line. So this is your state 1. So from here you are having a sensible heating. So there is no change in humidity. So you are reaching state 2, and from state 2 there is a humidification and heating because you are adding steam at 110 degrees Celsius. So you will reach state 3. So we need to find out the temperature and dry and wet bulb temperature at state 3. So the enthalpy at state 1 is 13.82 and your specific volume is 0.792, and your specific humidity corresponding to this is 0.0036. So with this, first we'll find out the mass of air. So mass of air is your volume flow rate into uh, 60. So this is meter cube per minute, 90 meter cube per minute. So into 60 divided by your specific volume, so 0.792. So that gives you, sorry, we're converting into hour, so that will give you 6820 kg of dry air per hour. So that is the amount of mass of air which is flowing inside. So by moisture balance we'll do a specific humidity water which is getting added. So omega 3 minus omega 1 will give you the mass of water which is getting added. So that is mass of air into the change in specific humidity, which is equals to 40 kg per hour. So mass of air is 6820 kg of dry air per hour. So from this we can find out omega 3. So we know omega 1. Substituting omega 3 is omega 1 plus 40 divided by mass of dry air. So this give you omega 3 as 0.00947 kg of water vapor per kg of dry air. So if you do an energy balance across the whole system, so m dot A H3 minus H1 equals so what is happening is what is inlet is m dot A into H1, and mass of stream which is coming, mass of water vapor into your enthalpy of water vapor plus heat added, and equals mass of air which is leaving. So if you rearrange it, you get mass of air into H3 minus H1 equals your heat added, which is 40.7 kilowatt. So we are converting into hour because everything is in hour basis. So divide into 3600 plus 40 into your enthalpy of water vapor, which is added at 110 degrees Celsius. So that enthalpy is 2691.3 kilojoule per kg. Substituting here, you can find out the enthalpy at state 3, which will come out to be 51.1 kilojoule per kg of dry air. So now we have located enthalpy and we also know the specific humidity. So with these two quantities we can now estimate the temperatures. So your dry bulb temperature is corresponding to this enthalpy and specific humidity is 26.5 degrees Celsius, and your wet bulb temperature is 18.1 degrees Celsius. So we have an air conditioned space is maintained at 27 degrees Celsius dry bulb temperature and 50% relative humidity. The ambient conditions are 40 degrees Celsius dry bulb temperature and 27 degrees Celsius wet bulb temperature. The space has a sensible heat gain of 14 kilowatt. So air is supplied to the space at 7 degrees Celsius saturated. So calculate mass of moist air supplied to the space, to latent heat gain of space in kilowatt, 3 cooling load of the air washer in kilowatt if 30% of air supplied to the space is fresh, the remainder being recirculated. So what is given is we have an air conditioned space, we have to maintain this at 27 degrees Celsius dry bulb temperature and 50% relative humidity. So that is fixed. So the ambient conditions are given. So that is can also be located, which is 40 degrees Celsius dry bulb temperature. So that is the incoming air, and 27 degrees Celsius wet bulb temperature. So the space has a sensible heat gain. So that is the amount of heat which is coming in, which is 40 kilowatt. So and we need to we have to supply the air at 7 degrees Celsius. So the properties are given. So outside is 40 degrees Celsius and 27 UL bulb temperature. The specific humidity for this case is 17.2 grams of water vapor per kg of dry air, and corresponding enthalpy of air is 85 kilojoule per kg of dry air, and the inside room temperature is 27 with dry bulb temperature and relative humidity 50%. So corresponding specific humidity is 11.2 and enthalpy is 56.1. So now we have to supply the air at 7 degrees saturated, so 7 and 100. Specific humidity corresponding to that is 6.2 and enthalpy is 23. So the mass of dry air supplied to the space is so you are supplying air at 7 degrees Celsius and the room is at 27, so it is heating from 7 to 27, and in that process it has to gain the sensible heat of 14 kilowatt. So using this we can find out the mass of air. So the sensible heat is 14, so multiply by 3600 to convert into R, divide by Cp into delta T will give you 2467 kg of dry air per hour. So this, the ratio of moist air to dry air in supply air is 1 plus omega, so it's equal to 1.0062. So this says that if you have 1 kg of dry air, so the mixture is of 1.0062 kg. So the mass of moist air supplied in the space is, so 1 plus omega 2 into mass of dry air, which comes out to be 2482 kg per hour. So that is the amount of air which is going to the room. Next is latent heat gain of space. So latent heat gain is nothing but the change in specific humidity, the heat added to because of that. So the mass of air, dry air, into this change in specific humidity into the enthalpy, latent heat of enthalpy. So initially it is at 11.2, the supply is at 6.2 and the room is at 11.2. So this difference is your specific humidity and mass of air into enthalpy change. So this gives you 8.57 kilowatt. So this is the latent heat added to the air. So third is for point 1, so cooling load of the air washer in kilowatt is 30% of air supplied to the space is fresh and the remainder being recirculated. So now we are mixing 30% of fresh air which is coming at 40 degrees Celsius and remainder is the recirculated air which is coming at 27 degrees Celsius. So if you see the mixture temperature then is mixed in 70 and 30% proportion. So the mixed temperature will be 30.9 degrees Celsius. So on the line joining the inlet to outlet temperature, we need to locate this temperature 30.9. So the correspondingly that enthalpy is 64.9 kilojoule per kg of dry air. So now the cooling load of the air washer is we need the supply temperature at 23. So how much it has to remove? So because the temperature is coming at 30.9, so corresponding enthalpy is 64.9 and the air which has to be supplied is at 23 kilojoule per kg of dry air enthalpy. So into mass of air, so this gives you a total of 28.71 kilowatt. So this is the amount of cooling load which has to be supplied by the air washer. So with this we have finished psychometrics, and I finished what I prepared for today. So next class we look at the compressors, refrigerant compressors, and some problems regarding to that. So this week we generally focused on mixture, basically the air and water vapor mixture, and we did some psychrometric processes and how to estimate the different properties when it's given. Two of the properties are given, and some examples on humidification and heating, cooling and humidification, and this example where your air is getting mixed and so on in a air conditioned space, how it's happening. So thank you, and we'll meet on next week for the refrigerant compressors. That will be the last class on the after thermodynamics week, and we'll also have a review class on Tuesday. I'll end the session. So meet you next week.